Okay, good morning, everybody. It's my great pleasure to introduce Dr. Ralph Kahn, a senior scientist in NASA Goddard Space Flight Center. I have known Ralph for probably over 20 years. The first time we met is actually during the Puerto Rico dust field campaign in Hawaii. And I was sitting in your car, I still remember that moment. So anyway, since then I have been seeing Ralph, and we see each other a lot in many meetings and panels and such. And Ralph received his PhD degree from Harvard University in 1980s. And then he spent 20 years as a research scientist and a senior research scientist at the JPL, where he studied climate change on Earth and Mars, and then later the Earth and the planetary atmosphere research element over there in JPL. He also is well known for his leadership for the MISR on aerosol tubes, and as well as the aerosol Plume-Height research and many other work regarding the aerosol impact on regional and global climate change. And he joined the Goddard Space Flight Center, I believe, is it in 2008 or
2007?
2007.
Yeah.
And Ralph has over 200 publications, and he's the chair of the COSPAR and also co-chair for Aerosat. And he's very active in many other international associations for satellite remote sensing of aerosols and clouds. And he received numerous awards, including the NASA Exceptional Service Medal, Outstanding Leadership Medal, Robert Goddard Award for Exceptional Achievement in Science, and then AGU Yoram Kaufman Award, and the William Norberg Memorial Award for Earth Science, and also last year, the Fellow of AGU, very prestigious one last year. That's a recent award. I'm sure he will have more work to come in. So, well, welcome, Ralph.
Thank you.
So, because he cannot use the Zoom, client Zoom in his computer, so I will move the computers to him. So let me see here. Try to get this set up here. Okay, Ralph, here you go.
All right, great. Okay, so I'll be talking primarily about analysis we're doing with the MISR instrument, the multi-angle imaging spectroradiometer. And I'll talk a little bit more about that in a few slides. But I'll also be introducing some data from other sources. In fact, I'll give a little historical introduction at the beginning here as well. You will note that in the lower right of most figures, there will be a reference. So wherever the work is published, which is almost everything here, you'll be able to follow up. So let's go to the next couple of slides here. Let's go to the next slide. So I wanted to start by giving you sort of a visceral sense for what we do with remote sensing. Some of you may have a very good sense of that already, but I'll do that quickly here. So Jun, next slide. Next slide, yeah. So this is a dust storm from the surface. This was one in Phoenix, Arizona in 2011. And that's what the dust looks like from the surface. If you go to the next slide, please. And that's what it looks like from space. This is now off the coast of Africa. And you can see the color. It gives you some clue as to where the dust is. It looks a bit different. Okay, the next slide. Now that's a wildfire. This is a fairly recent one that actually, I think it's still burning, the bootleg fire in South Central Oregon. You actually may be getting some smoke from that fire. And the next slide will show you what it looks like from space. This is now in Alaska from 2004. The red dots are thermal anomalies. They're hotspots that are detected in the MODIS data set. And then you can see the pall of smoke, and you can see some clouds surrounding that. And again, you can tell from the color where the smoke is. And that, I just key that into you because that turns out to be an indication of something important we can do from remote sensing. Okay, the next slide. Okay, this is a volcano. This is Mount Etna. And I didn't have a ground-based observation, but the lower picture was taken from the International Space Station with a fairly high-resolution camera. So it looks kind of like you'd be looking at it from an airplane. And then the MISR and MODIS observations of the same eruption are shown at the top there. And so you can make a comparison and see the kinds of detail you see and the kinds of detail you don't see from space relative to what you can see from an airplane or from the surface. Again, the red circles here in the MODIS image are the thermal anomalies, the hotspots. Okay, the next slide. All right, so I like to show this slide because I think it is the first published example of how aerosols, airborne particles, in this case dust from North Africa, has been observed from space. And so this was an image taken in June of 1967, and it was published in 1970. And this bright area with the white arrow in the lower right image, that's the dust plume. And in the upper left, you'll see a mapping of that plume in a sequence of images from the ESSA-5 satellite. This was a Vidicon camera, a relatively crude camera by today's standards. And you can see the fiducial marks in the image in the lower right, those little T-like and angle-like shapes there. This is on the camera giving them some information about the way in which the image is parsed out in space so that they can rectify it and make it clear. And then in the upper left, you can see the historical transit of this over 5 or 6 days from North Africa to the Caribbean and just north of South America. And that was the first published example of doing things from space for aerosols. The next slide. Okay, so then came the AVHR, the Advanced Very High Resolution Radiometer. A whole series of these have been flying. This was an early one. This paper by Rudy Hussar and Joe Prospero. By the way, Joe Prospero was the guy who kind of spearheaded that early transit from North Africa of dust into the Caribbean. And he's done a whole career of study of that phenomenon. So this was Rudy Hussar and Joe Prospero and Larry Stowe put this paper together in 1997. And you can see what they've done is they've estimated the aerosol amount from the brightness, and they can only do that over the dark ocean surface because the aerosol has to stand out. And this will turn out to be one of the fundamental problems in doing retrievals from space is that you have to account for the surface. And so if you have a dark uniform surface like the ocean, that works pretty well. And so this was the first systematic global set of observations. And what you can see here is in the northern winter, you can see biomass burning and a small amount of dust coming off of West Africa and Central Africa. And then in the northern summer, in the lower part, you can see that there's a lot more dust, and there's smoke from Central Africa now, and there's dust from North Africa and also the Middle East. You can see pollution off China and off the east coast of the United States and Eastern Europe. In any case, only over water. These retrievals were done only over water because they could not account adequately for the land surface in the imagery. But where you have good imagery, they've got good data. And so this was, again, the first global sense of what we had. The next slide, I have to go a little quickly here. So another technique that was used uses the ultraviolet instead of the visible. Everything I've shown you up to now is visible, and most of what I will show today is visible. But in the UV, the surface tends to be dark. And of course, you guys probably all know that the sky is blue because of Rayleigh scattering, and the Rayleigh scattering of the atmospheric gas obscures the surface. And if the aerosol, especially if it's elevated, will be appearing in the UV imagery in absorption features. So what happens is there's the upwelling atmospheric scattering, gas scattering from below, and then the aerosol above it will absorb. And so this is work that was done by Christina Su. And you can see here the dust over Central Asia. So now they're doing dust retrievals over land and water using this UV absorption technique. There are some limitations. Every measurement has limitations, but the limitations here in the UV is that if the dust is, or if the aerosol is very near the surface, then the atmospheric scattering, the gas scattering will fill in and you won't see it. The other thing is that to get a quantitative estimate out of this, you need to know the UV properties, the UV absorbing properties of the particles, and you also need to know the elevation of the particles. And those are two difficult things to get. So this tends to be a qualitative, what they call an aerosol index indicator. Nevertheless, it was the first way in which we could, with some reliability, get information about aerosols over land surfaces from space. Next slide. Okay, so in the year 2000, actually it was December of 1999, we launched this Terra spacecraft, which was the first big spacecraft for the NASA Earth observing system. The spacecraft itself was about the size and weight of a full-grown Indian elephant, so it's huge. And it had 5 instruments on it. It's still operating, and all 5 instruments are still downloading data. And the 2 that I will be talking about the most are MODIS in the front of the spacecraft, which is in the upper left, and MISR, which is facing downward toward Earth at the bottom of the spacecraft. And then there's MOPIT, Ceres, and Aster as well. I'm not going to talk about those today, but if you're interested, there are neat stories about them as well. And in the lower right, you can see the launch. We were all there at Vandenberg Air Force Base, which has been renamed something else now, I think. Oh, Vandenberg Space Force Base. All right, anyway, but that was the launch. December the 18th in 2019. Our first light with MISR and MODIS was on February 24th of 2000. So we'll go from there. Next slide, please. Okay, so this is the MISR. This is an illustration of the spacecraft with the MISR observing strategy illustrated here. MISR, the instrument itself is, I've got an image of it from the clean room at JPL when it was being tested in the upper right here. It was about the size of a steamer trunk, and it weighs about 350 pounds. I pointed this out in the press conference that we had when Terra was launched. Unfortunately for me, the steamer trunk analogy did not go over very well because at the time the popular movie was called Titanic. Nevertheless, people get an idea of both the size and of the instrument, and also from that elephant analogy, what the spacecraft is like. So this instrument, MISR, has 9 cameras, and they're pointed in 9 different directions along the orbit paths. This is an orbit path that takes it very nearly over the poles. So it's a polar orbit. It's called sun-synchronous, which means that it crosses the equator at about the same time every orbit as the Earth rotates below it. And it's about 10:30 or 11 o'clock in the morning, local time, when it crosses. Now, each of these 9 cameras has 4 line arrays at 4 different wavelengths. There's a blue, green, red, and an 867, 866 nanometer channel in the near infrared. And the swath is about 380 kilometers wide. And in the course of 7 minutes, as the spacecraft orbits overhead, these 9 cameras successively image the same locations. So we get effectively 36 4 times 9 strips of data from roughly pole to pole. In every orbit, we have 14.75, about 15 orbits per day. We get global coverage about once per week. So that's the data we're talking about here primarily. Our sister instrument MODIS has a much wider swath of 2,300 kilometers as opposed to 380 kilometers. And so they get the Earth about once every day or two, less at the equator because it's in a polar orbit. But they have 36 channels, just like MISR does, but they're all single view. So they have multispectral bands, but not multi-angle. Next slide. Okay, so one thing we can do with this multi-angle data is to use the parallax to get the heights of clouds and aerosol plumes. And you see in the lower right here an illustration of how parallax works. There's the sun and there's a camera, And in the image to the left, you can see there's a camera pointing at one angle, and then the image to the right, there's a camera pointing at a different angle. Of course, we get both of those. We actually get 9 of them. And the projection of the camera image to the surface, you can see, is illustrated in that little red line that goes down to the surface. It moves because the cloud or the aerosol plume is above the surface. Now, if you think about it, the closer the plume is to the surface, the shorter that distance along the ground will be, whereas the higher the plume is, the farther that distance will be. And from that, we can geometrically determine the height of the plume. Because we have 9 cameras and 7 minutes, we can actually also observe the proper motion of contrast features in the plumes. And so we can estimate the motion vectors. And so we can do a correction to the height for the proper motion, because if the contrast features move in those 7 minutes and we don't take that into account, we'll get the wrong height. So this is an illustration here from a volcanic eruption that occurred in April of this year at La Soufrière in St. Vincent Island in the Caribbean. And in the upper left, you can see this is a nice MODIS context image. You can see the MISR swath is narrow, but it captures the volcano itself, which is that little red triangle. And the yellow outline here outlines where the plume features stand out about above the surface and clouds to a large extent. And so we do our retrieval in that little area near the volcano within the MISR swath. And in the upper right, you can see the plume heights, and you can see this volcano erupted very high. It was up 22 kilometers near the source, and then of course it diminished somewhat downwind. And in the lower left, you can see a profile view where the volcano is at 0 on the left side of the plot. The blue dots are the wind-corrected heights. The red dots are the non-wind. So if you ignore the proper motion, you get some diversity of points here. And then the green, which you can just barely see because there's surface now, that's the surface. So that's how I'm going to show a number of examples of these plume heights. But this was La Soufrière volcano, and our results here, both the particle properties, which I'll get to in a few minutes, and the heights, turned out to be very important for the disaster response folks. They were very excited about this because it allowed them to make a more confident model predictions of where the volcanic plume was going to go downwind, because they could initialize with the proper height. And so they actually sent us a thank you note at the end for having provided that information. Next slide. Next slide. We need to go. Okay, so what do we do with these heights? Well, I've had many students, and at JPL there were many students. At the University of Maryland, we've had many students. And also my colleague Maria Vel-Martin, who led this particular part that I'm showing now, also has had students, and they've digitized the plumes. You need to outline where the plume stands out above the surface, as I showed in the previous slide. And so we've had tens of thousands of plumes of smoke and of volcanic plumes and of dust plumes that have been digitized by the aggregate of all of us that have been working on it. And so Maria led our paper in which we put together a climatology, a global climatology of smoke plume injection heights. So there are 23,000 plumes in this. You can see the dots are where we have our plumes. They were all digitized with this interactive software, and the data set is actually available, and the website is at the bottom of the slide. The next slide, I'll say a little bit more about the plume. So here's what we do. We stratify the data by the altitude, obviously, because that's the main thing. The region, the data are all sorted by regions. We have some information about the ecosystem, so what was burning at the surface, and of course the season as well. And you'll see in the upper left here an example of one of the profiles. And so what we do is we make a statistical summary, and there are two ways we can do that. One of them is that we can do it just by the number of pixels at a given height, and the other is that we can weight each pixel by the optical depth, by the aerosol amount, which we can also estimate from MISR. And so you see both the pixel weighted heights and the optical depth weighted heights as two histograms here, vertical histograms in the upper left. And then below that, you can see how one can do various studies. This is, for example, June, July, August, averaged over several years. And you can see the distribution as a function of longitude. And then December, January, February, you see the differences where the burning occurs during different seasons. The next slide. So on a global basis, one of the important questions to ask is whether the smoke is injected above the boundary layer. So the atmosphere has a boundary layer in most places. And on Mars, there's no boundary layer, actually, it turns out, or at least not in the same sense that we have on Earth in terms of the temperature profile. But on Earth, we have a boundary layer, typically. And the first order question one asks about injection of smoke or any aerosol into the atmosphere is, does it get above the boundary layer or not? Because if it gets above the boundary layer into the free troposphere, the winds are steadier, the aerosol will stay aloft longer, it'll travel farther, it'll have a very different and generally greater environmental impact. And so what we've got here are the plots from our climatology, again from the same paper, for 2 seasons, with the fraction of cases that inject above the boundary layer. And we use 2 definitions of boundary layer because it's really hard to get it from a model. One was to use the MERA2 reanalysis, which is a model that's constrained by observations. And so you see that in the high latitudes, mostly the boreal forests, especially in the winter over Siberia and North America, that's when the injection occurs preferentially above the boundary layer. In the summer, it's distributed to a bit more lower latitudes. We also just said arbitrarily, let's call it 2 kilometers, and let's see where the injections are above 2 kilometers, and that's the lower panels. And we found that somewhere around 18% of the boreal forest fires inject smoke above the boundary layer, which turns out to be turned out at the time to be a bit of a surprise. It's a lot of smoke, and some of it gets even higher than that. Okay, next slide. So a couple more things we've done with the plume heights before I get into particle properties. I had some undergraduate students, I have them regularly at the University of Maryland, and we do projects, and CJ Vernon and Ryan Bolt did some work with me, and Tim Canty, one of my fellow faculty members, looking at what happens if we do or don't initialize a famous model. This is the high split, the NOAA high split model, with the proper injection heights from MISR, or just use the nominal model injection heights. And so this was one of those cases. This was a fire in Alberta, Canada in 2016. And the upper left is initialized with the MISR injection, and the upper right with the high split injection. And in the lower left, you can see the difference, which if you live near the fire here, it makes quite a significant difference right in there. Some of the differences are even bigger, but this showed one example. The next slide. Okay, so another thing we did, this was one of Maria's students, Laura Gonzalez Alonso, and so what we did for this was we looked in detail at the climatology for the Amazon region. And so in the left here, you can see parsed out by different surface types, forest, savanna, and grassland. We have in the top row of plots, the MODIS thermal anomalies. Remember those red dots and circles that we had? Those are the red lines. And then the MISR heights in the black, and you can see that as you go through the season, each one of these panels goes through 5 months of season, the fire intensity increases because the land dries out during the dry season. The boundary layer height is mapped in the second row there, and the atmospheric stability structure, those two are often closely related. And then the optical depth, the amount of aerosol in the bottom row. We also looked at on the right side here, I don't have time to go into it in detail, but we looked at drought years and wet years and how the behavior varied. It's a little bit of a complicated story, but it's a nice paper if you care to read it. The FRP and the height, the fire radiative power, the anomalies of the thermal infrared tend to increase as the fire season progresses. We talked about that. The optical depth tends to increase, and the height tends to decrease for forest and savanna fires during drought years. So this was a surprising result. And the reason turns out to be that during dry years, the fires actually penetrate more into the root area. And so you get more smoldering fire and less flaming fire as a percentage of the total. And smoldering fires tend to have lower thermal anomalies. They aren't, the brightness temperature is measured from space is lower. The smoke tends to be more brown carbon and less black carbon. And the injection heights aren't as high. Okay, next slide. Next slide. Okay, so I've talked about a lot about heights, and since I'm a satellite guy, I have to say something about the lidars, because the lidars, CALIPSO lidar is probably the premier instrument for getting heights. It's more sensitive than MISR to height, but the swath is 100 meters. So it's just an active sensor. It sends out a laser beam and then measures how long it takes to come back. And so it gets the height very sensitively, but only over a very tiny curtain. And so you can see in the upper left here, the curtain for this particular plot case is mapped out in those colors. And the plot itself here in the middle shows some maritime aerosol down near the surface. There's dust and there's pollution. The pollution is aloft in this case because we're looking largely over the ocean. And my colleague Hongmin Yu wrote the paper on this in 2010. And so at the bottom here are, for different seasons, the vertical distribution as averaged over the eastern China region in this case for dust and for all particles. That's the yellow and the blue respectively. And you can see the seasonal variation in the regional averaged vertical distribution of dust. And you can see that the dusty season is in the spring. And there's much less in the summer, a bit in the fall, and you can see, anyway, there's a lot of stories here too. Again, I'm trying to give you at least a précis of some of the things we do with the satellites. Okay, the next slide. Okay, so one thing I have to say about these measurements of aerosol vertical distribution is that different techniques are sensitive to different things, and as a result, they will get different heights. So MISR looks at the contrast features in the plumes in the imagery. And so we kind of sample sort of in the middle. The LiDAR looks at the backscatter from individual particles, and so a very thin aerosol layer will be captured by LiDAR, but MISR won't actually see it until you've gone deep enough into the plume to get a contrast feature out of it. So LiDAR tends to skew a little higher than MISR, not because either one is wrong, but because they're measuring different things. Similarly, the passive infrared techniques, which I don't have time to talk about, but it's done for MODIS, for example, and my colleague Alexei Lepustin has a product using that to get the heights of aerosol plumes. That tends to sample even deeper and sometimes actually captures the ground below as well. So those heights are skewed lower. So if you're comparing these things, you really need to think about what the information content is of the measurements that are being made, because they may all be right and all be different, and there's actually information in the differences between the different measurements. Okay, the next slide. Okay, so now I'm going to talk about Aerosol-Type. That's the other unique aerosol product that we have from MISR. And Aerosol-Type is, is it maritime aerosols? Is it dust? Is it smoke? Is it pollution particles? That's the kind of thing we're talking about here. And one can get fairly specific about the detailed properties, which is really of great import for a variety of things. We'll get to that at the very end. But right now, I'll just sort of summarize in broad detail, in broad scope, source attribution, where the aerosol is coming from. Getting the particle type will tell you a lot about that in most cases. One wants to know how much light is absorbed by the aerosols, because that can affect the atmospheric stability structure and affects convection and clouds and many things. So again, Aerosol-Type has some information about the aerosol light absorption. Also the particle hygroscopicity, what the tendency of the particles is to absorb water vapor. And that's important if you want to make clouds. To make a cloud particle under almost all circumstances, except if it's very cold, you need to have a particle to start with. And so the more hygroscopic the particles are, the more hydrophilic, the more likely they are to collect the water vapor, the more likely you are to make a cloud. The mass extinction efficiency, this is a quantity that you need to use to relate the measurements we make from remote sensing over a global scale, which are optical measurements, with the mass of the particles, which happens to be the way in which climate and air quality models bookkeep their aerosols. So you need a number that tells you how much mass to assume for a given optical amount, optical depth. And that's what the mass extinction efficiency is. And that, of course, varies with the particle properties and with the amount of water vapor and the relative humidity and other things. But particle type gives you some clue as to mass extinction efficiency. Okay, the next slide. So here's the first example. This is a historic example I wanted to show. This was in 2016, in the fall sometime. Oh, yeah, October, it says on the slide even. We happened to have an observation at the time when the Allied troops were marching in Iraq, in northern Iraq, toward Mosul to liberate the city from the Islamic State. And in the retreat, the Islamic State set fire to oil fields and to a sulfur factory. And so down at the bottom here, well, first of all, you can see the nice context modus image in the center bottom. And you see there's white smoke from the sulfur factory, and there's black smoke from the oil fields. And we also have the Plume-Heights here. I'm not going to talk about those in detail, but I wanted to show you one example. You really have a lot of information about particle properties from the imagery, just by looking at it. But we're going to get more than that in the next couple of slides. I'll show you how we do that. The next slide. Okay, so with MODIS, you just have the spectral information, just different wavelengths. And it turns out that bigger particles will scatter visible light more uniformly as a function of wavelength than smaller particles. So if the change in the apparent aerosol amount with wavelength is very steep, those are smaller particles. And so my late colleague, Yoram Kaufman, used that information and created this color bar in the middle of the figure, where if there's very little aerosol, he colored it blue because there's not a lot of information. If, on the other hand, there's a lot of aerosol, enough aerosol, I should say, and the spectral behavior of the optical depth is flat, it's got a green color. Those are bigger particles. And if they have a steeper behavior, then it's that red particle, the red color, the steeper change of optical depth. And so the idea was that things like smoke and pollution particles tend to be smaller, whereas desert dust tends to be larger. And you can see qualitatively in these monthly plots all around that the dust off of North Africa tends to be greener, and the biomass burning in Central America and Central Africa tends to be redder. So that's qualitative information. It's mostly good over water, actually, in terms of reliability, but you can do the retrievals anywhere. And that's what we have from MODIS. Now, the next slide. CALIPSO does something about particle properties too. They make a whole bunch of assumptions, and the assumptions related to the surface type that produces the aerosols are circled in green here, desert and ice and tundra and so on. You need to input that. They use two pieces of information. One is the backscatter of the particles, basically how bright they are when you bounce a laser beam off of them, and then something called the depolarization. So it's an attribute of radiation, electromagnetic radiation, that it bounces differently in different planes. And without going into a lot of detail, big particles depolarize more than small particles, which tend to polarize. And so using those two pieces of information plus the other surface properties and so on, they parse out 6 types of aerosols. Again, it's fairly qualitative, but it's very useful. Next slide. So with MISR, with the multi-angle information, okay, the key angle here is this angle theta shown in the upper left. It's the scattering angle. So the sunlight comes in and it hits particles and then it bounces back toward the camera. Now remember, we have 9 cameras pointed in 9 different directions. So we sample a range, excuse me, a range of scattering angles. The horizontal axis in all these 3 other plots is the scattering angle. And we sample in mid-latitudes from about 60 to 160 degrees. So it's a good part of this curve, of these curves. And I've got here from some early papers that we wrote, the variation in the scattering as a function of angle for different size particles, particles with different light absorption, and particles with different general shapes. And so you see there's information there because there are differences. They're all systematic differences. And we did a lot of studies to understand that behavior and how it related to actual particles in the atmosphere. So the next slide is an illustration. So this was from a fire at Los Alamos in New Mexico, just shortly after launch. And so I've got these 3 panels here, which I processed with exactly the same radiometry. So the first thing you see is that in the nadir view in the middle here, it's a lot browner than the other 2. And that's because we're looking straight down through the atmosphere. And so you see a lot more signal from the surface and less from the atmosphere. The other 2 are in 60 degrees forward and 60 degrees aft. And if you look on the left side of those 2 images, you'll see a little bluish plume. Okay, so the first thing you know is that you have information about the amount of aerosol in the atmosphere by how much of a change you get in the viewing ability of the surface as a function of these angles, because you see more when it's a steeper view in the middle and then less when you're looking at a more slant path. The next thing you see is that not only do the plumes stand out, but they actually look different in the 60 degree forward and the 60 degree aft. So that's the angular information that's telling you something about the particle size and the particle light absorption. So particle size, particle amount, and particle light absorption. So the last thing I want to show, and this is a little harder to see, is in the right part of these panels, you'll see in the upper one a kind of white wispy thing coming off of the right side there. And if you look at the bottom image, you'll see that that wispy thing is way up at the top of the image now, a little bit farther to the middle there. It's there you go. That's it. So you see how that moved. That's the parallax. So now you can see how the height works. That's an example. Okay, the next slide. So here's an example of results. The upper one here is smoke particles off the Yucatan Peninsula in Mexico. And I've got the 70 degree forward view image there on the left, and then the optical depth, and then the angstrom exponent, which is that spectral dependence of the optical depth, which tells you something about the size, and then the fraction that's spherical. And you can see these are small to medium spherical particles. At the bottom is dust blowing off of the Sahara Desert. The color bars are the same, and you see these are now large particles, looking at that 3rd panel, and the 4th panel, they're non-spherical because dust tends to be non-spherical. Okay, moving on. Okay, so we can do this globally. Barbara Gately and I had a comprehensive paper on the aerosol type discrimination from MISR. You need to have a certain amount of optical depth of around 0.15 or 0.2 in the mid-visible, which is a modest amount, but not a trivial amount of aerosol in the atmosphere in order to be able to really get particle property information. The best place to look for particle properties, of course, is in plumes, like volcanic plumes and smoke plumes. So the next slide. Okay, so remember I showed you the La Soufriere volcano, the heights. Well, these are now the particle types. And this was another part of what we did to help out the disaster response folks, because you can see the particle amount in the upper left here, the optical depth. There's a lot of it, a lot of smoke. Particle shape, they're mostly non-spherical, and the particle size is fairly large. There's a low angstrom exponent, which means the slope of the spectral dependence is small. So they're large particles. Large non-spherical particles in a volcanic plume means ash. Okay, so we know that volcanoes tend to produce sulfates, sulfur that turns into sulfates, oxidizing and hydrating in the atmosphere, and ash. Now, sulfate is an air quality hazard. Ash is not only an air quality hazard, but it's also a hazard, a risk to aviation. And so we were able to tell them that this was primarily an ash plume and that they had to be careful about airplanes flying into it or near it. So that was part of that story. Okay, the next slide. We'll talk a little bit more. Okay, a quick summary about particle types. I didn't have time to emphasize each one of these points, but we get information about size, shape, and light absorption or indices of refraction. It takes a further interpretive step to get to the chemical composition. So we can say they're small, spherical, light-absorbing particles, but to say that they're smoke requires another set of assumptions. That's important to remember when you're doing that, because the confidence level goes down as you do that. The sensitivity to particle properties is much more dependent on the amount of aerosol than just retrieving the amount of aerosol by itself. So you can get the amount with great confidence, and the particle properties are harder to get. You need more aerosol to do that. There are a whole lot of things that need to be looked at when you're doing this, and in the research retrieval algorithm that Jim Limbacher and I have developed over many years now, has improvements in calibration, surface representation, particle microphysical properties. Data for validating the particle properties is much more sparse than data for validating the optical depths, the amounts. So, okay, next slide. Okay, one other caveat about satellite data: it's not perfect. You can't always get what you want, as I have at the bottom of the slide there. So here are some examples. This is now monthly global data for 1 month in 2018, August 2018. And you can see the artifacts in the data here in terms of coverage. Where there's complex terrain, like over the Himalaya, you can see that we don't have good retrievals. There are clouds, and when there are clouds, then you can't do a retrieval. Where there's snow and ice, you can't do a retrieval. Like during polar night, you can't do retrievals. And so those are places where, so this, so I mentioned this in part because I know Greg Carmichael is here and Junwag. They're both very much into modeling, and models have a very important role to play in taking our data and turning it into a global picture that fills in the gaps. So that's one of many important roles models play, and I wanted to just emphasize that here. Okay, now we'll go into examples. Next slide. All right, so people who don't do volcanology don't necessarily know that about a dozen volcanoes are erupting on the Earth at any one time. It's not a rare phenomenon. And they're actually, we've marked off here. So I have a postdoc, Verity Flower, who is a volcanologist. And that was a very smart thing I did because she knows a lot about volcanoes. And so we've done a whole lot of volcanology from space using our plume information and so on. And this slide here illustrates where the distribution of volcanoes is. Those stars, those pink stars there, I think there's 17 of them. Those are places where a gigantic eruption is possible at some time. The ones that are circled in yellow are the ones that are monitored regularly. The ones that are circled in red are monitored occasionally or somewhat. The ones that are not circled are not monitored suborbitally at all. Okay? Okay, the next slide. So we looked at some of these volcanoes from space. The Kamchatka Peninsula, which is on the east end of Siberia, is a very volcanically active region. There are many stories in this, and Verity and I wrote a whole series of papers about this. We're just going to talk about the most southerly of the volcanoes highlighted here, Karimsky volcano. You can see that at the bottom. We've got one example. This was one day when we had eruptions on 5 of the volcanoes all at once, January 6, 2013. It was one of our golden days in that respect. And you can see that we have the height retrieval at the very bottom there. But let's go to the next slide, and we'll get into some detail here just so you can see how much information we have. So there are 2 kinds of things we can say from the particle properties in these plumes, and because they're optically thick, there's a lot of information. One of them is we can trace the plumes downwind and see how the particles evolve during an eruption. And the other thing we can do is we can compare one eruption to another. So in this case, we have Karimsky volcano on 3 days, and on the right here, there's Halaharan volcano in Iceland. Now, Halaharan is a volcano that produces sulfur. It's very famous for its sulfate plume. Karimsky, on the other hand, produces mostly ash, and the ash has more or less light absorbing properties. And so you see the different colors here in the Karimsky plume. These are different images of the plume with the particle properties colored in. And the gray are ash particles, and the purple are ash particles that are more light absorbing. Next slide. So we can take that information and we can actually, because we have satellite data regularly, we can make these little cartoons showing how much ash and how much sulfate and how much absorbing aerosol we have in the plumes as a function of time. And you see in this plot, we actually have 3 kinds of information. Those cartoons at the top are the particle types in a cartoon form, from what I showed you in the last slide. These purple vertical bars kind of in the middle of each timeline are the vertical heights, the heights that we get from the MISR retrievals. And the dots at the bottom are the MODIS thermal anomalies, so you can get some idea of the activity. The next slide is just actually a bump. Yeah, okay, so we're gonna just concentrate on this little area where it goes from ash to sulfate, and we'll tell you the story that we were able to tell. So the way we can tell a story is we have the retrieved effective particle size. I've told you how we get that. And we get the retrieved effective particle absorption. And we can see how that varies from plume to plume and within the plume from early to late age. And so if we see, for example, the particle sizes not change, the retrieved effective particle size not change as a function of downwind, but the optical depth goes down, that suggests that we're getting particle deposition that's independent of the size. On the other hand, if the optical depth goes down and the particle size diminishes, then it probably indicates that there's size dependent particle deposition. If we see an increase in optical depth and a decrease in the particle size, that could be uniform, that could be new particle formation. On the other hand, if the optical depth stays the same and the particles get bigger, that could mean that there's volatiles depositing on the aerosols, or they could be absorbing water vapor from the atmosphere and growing. So we can deduce something about the processes. And the next slide, we'll talk about how, again, having a volcanologist on my team was terrific because we were able to tell this story here from those 4 plumes that we analyzed over this period in 2007. We started with a capped volcano and relatively low thermal activity, and then it started erupting, and initially it was erupting with volatile, poor aerosol. And then gradually the aerosol, the magma came up, fresher magma came up, and then at point 4 here, we actually get this fresh magma, which includes more volatiles. And so all of a sudden you see the sulfate showing up. And that continued until we had depleted the fresh magma, and then it got quiet again. So that's just one example of an interpretation. The next slide. Okay, so this is Halaharan. I just wanted to show you how different the plots are for the particle types when you have a sulfate volcano here. And we've added one more data set. Right below the cartoons, there are these little blue X's, and those are from the UV instrument called OMI, and what they're measuring is the SO2, which is the precursor to the sulfates. So the SO2 gas gets emitted, and then it turns into sulfates as it ages in the atmosphere. Okay, the next slide. Okay, so we were just showing off here. This is the Grimsvatn volcano. It had a brief eruption in 2011 and actually erupted 3 plumes at different heights. And so you can see them sort of colored by heights in the left. In the bottom middle, you can see the profiles. You can see the 3 plumes. And I've got them outlined here in the right. And I should just note the atmospheric stability structure is plotted in orange. I just want to call your attention to the fact that there's the boundary layer, and then there's this other layer of relative stability up higher in the atmosphere, right up there where Jun's pointing. So the next slide will show a cartoon of what we interpret that as being. Next slide. Okay, so here's what we were looking at. We had 3 different plumes from this one volcanic eruption. The particle properties are shown on the left, and the cartoon showing the plume distribution is on the right. Now, down near the surface, we have large non-spherical particles. So the ash particles kind of hug the surface. In the middle of the atmosphere, we have small to medium spherical non-light absorbing particles. Those are sulfate particles. And way at the top, this is up at the tropopause. Okay, so that middle plume is where that stability, that maximum in the mid-tropospheric stability occurred, and then the umbrella here is at the top, and that plume actually has a mixture of both the sulfates and the ash, and that's because the volcanic eruption was extremely energetic, and it blew both ash and sulfur up to the top. So just to show you this, all that information just from the remote sensing. So you think about all those volcanoes that aren't observed from space. This helps. Next slide. Okay, so wildfires, a quick example here. Katie Jungen-Noyes was a graduate student working with me. She's now a postdoc in my group. And we were participants in a field campaign called FireXAQ in the summer of 2019. And we had one golden day, one day when MISR flew over one of the plumes that they were sampling with the aircraft. That was the Williams Flats fire on the 6th of August, 2019. We had 2 plumes. One was the North Plume and one was the South Plume. We've got the heights here. The one thing I want to show you about, well, 2 things I want to show you about the heights. One is the South Plume injected about 2 kilometers. The North Plume was more energetic. It injected up to about 2.5 kilometers. And I have a red arrow on the right side there of the plot showing where the plume seems to have touched the surface or reached the surface at about 40 kilometers downwind. Next slide. Next slide. Okay, so you can see, so we divided this plume up into 4 regions, the North Plume into 3 regions, and the South Plume just into region 4 by itself. Because we have the motion vectors, we can actually assign time horizons to how old the plume was at these different points downwind. So we're up to 200 meters down, 200 minutes downwind for the most aged part of the plume we're studying here. The optical depths you see in the upper left. The highest concentration near the source, and then it diminishes downwind. But you look for the South Plume in region 4, it's pretty uniform. For the North Plume, it varies and it goes down dramatically as a function of distance. You look at the single scattering albedo, the brightness of the particles in the upper right, you see that near the source, the particles are very dark, and then they get brighter, and then they get brighter still. By the time you get to region 3 there at the end, they're probably mixed a lot with ambient clean aerosol. At the bottom, the particle size, you see there are small particles near the source. They stay small in region 4 for the South Plume, but for the North Plume, you see they get bigger. So this is where we inferred that there was deposition occurring on the particles from volatiles. And we have aircraft data that actually prove that show that these interpretations I've mentioned are correct. The next slide goes even further. And so now I've still got the angstrom exponent single scattering of it. Now you can see the black smoke. We inferred that occurred near the source and pretty much consistently for the South Plume. For the North Plume, we see that brown smoke starts showing up in region 2. So this is all in our paper in atmospheric environmental research in 2020. You're welcome to have a look at it. It's a neat story. Okay, the next slide. Okay, so I'm up to my very last topic. I'm sorry, I'm running a little over, but I want to talk about some big picture thing here now that I've given you some illustration of what we can do with the satellites. And that is that from my perspective as the aerosol scientist for MISR, I don't think satellites have all the answers. I've never thought that, and I've been an outlier in the satellite community at times because of that. I think we can provide frequent global coverage, snapshots, and sometimes continuous from geostationary. We can get aerosol amount, and we can map out the aerosol types and the plume heights. We can't get the detailed microphysical properties, and we can't fill in the gaps, and we can't make predictions. The suborbital data is what we need in order to get the microphysical properties, the detailed mass extinction efficiencies, hygroscopicities, particle light absorption that you cannot get from remote sensing. Even if you can do some loose constraints on some of those things, you cannot get them at the level of detail you need in order for models to do the job of predicting the future and estimating the aerosol forcing, which is what is needed from aerosols in order to contribute to predicting the future. So if you go to the next slide, and this is my last little topic. So this puts that picture together. You probably are familiar with the IPCC, the Intergovernmental Panel on Climate Change report, and the aerosol indirect effects, which is the effects of aerosols on clouds. That's considered very low confidence. We don't really know how much forcing that is. For what they call the direct forcing, which is how much the particles scatter and absorb light, they claim it's high confidence. In 2013, they claim that. But in the previous IPCC report, which was 7 years earlier, they did not say that. And in fact, there was really no advance between in that respect in our understanding of aerosols between the most recent IPCC report and the previous one. So I'm a little skeptical of that high confidence. In fact, I'm quite sure that it's not high confidence. A paper by Steve Schwartz, we talked about how knowing the forcing is critical in order to be able to predict what the temperature response is. So the simplest way to contextualize the relationship between the forcing, which is on the left of this equation here, and the temperature response, which is on the right of that equation, is this climate sensitivity. And it's a neat story. It's a whole lecture in itself. But I'll just say that that climate sensitivity, the way in which we get that is we know what the temperature history is, and we think we know something about the forcing, and so we can deduce the climate sensitivity. However, if you don't know the forcing, or if you're unsure of it, then the climate sensitivity uncertainty goes up, and that's the situation we're in. So here's what we need to do. Next slide. Okay, so all we really need is a small aircraft, but it's not that small. It's a 2-engine plane or something of that size, to characterize statistically the particle properties for the major aerosol air mass types globally. And this is needed because models have to assume the particle properties in order to model the direct forcing, how much the particles absorb and scatter light, and also the indirect effect on clouds. They need those properties, and we can't get them from remote sensing alone at the level of accuracy we need. For the satellite retrievals, we again have to assume the particle properties in detail. We can get the type in a general sense, but not the detailed properties. And there again, those microphysical properties from different sources can be gotten best from in situ measurements. The other thing that's really important and kind of interesting is that we talked about the mass extinction efficiency. That's the quantity that allows you to use the satellite data, the optical depths, as a constraint on the model aerosol mass. And to do that quantitatively, you need a mass extinction efficiency. So this is what we talked about doing. The next slide. So I've already said most of this. These are the quantities we need, and these are either unavailable or can only be gotten in a very crude way from remote sensing. One thing I didn't talk about is CCN properties. It turns out that because cloud condensation nuclei, the number of particles matters. The small end of the CCN spectrum is too small to distinguish with remote sensing from molecules of air. So you need to measure those in situ as well. The critical point here is that acquiring such data is feasible because unlike the aerosol amount, which varies a lot from year to year and day to day, the microphysical properties tend to be repeatable from year to year for a given source in a given season. So if you're burning vegetation in Alaska, that some years there's a lot, some years there's a little, but it's the same vegetation in the same environment, so the particle properties tend to be the same. The same is true for Siberia forest fires, although the Siberia vegetation is different, so the particles are different, but from year to year, the particle properties tend to be repeatable. So you don't have to measure them all the time, you just have to measure them well once. Next slide. Okay, this is an example of how the models are all over the place and the assumptions about mass extinction efficiency for different particle types, but I'm not going to go into this now because I've run over. So the next slide. Okay, implementation. One has to be systematic about this, but it's quite feasible to do. It doesn't require a big aircraft. It's comparable in cost to one satellite instrument or something, and it would add value to all the satellite data on aerosols and the modeling everywhere. Next slide. And if you're really interested in the details, you can read this. There's heritage for this. NASA's done a variety of things that are similar in certain ways. The measurements that are needed have all been made in the past, but they've never been made systematically for a given aerosol type, frequently enough for us to get the probability distribution, the distribution of values and the uncertainties. You have to measure over and over again until you get it right, which means a different kind of campaign than we usually have. The next slide, I think I'm getting to the very end here. Yeah, this just summarizes things I've already said. This is required to close the aerosol forcing uncertainty gap, which we talked about a couple of slides ago. And finally, last slide or next. Okay, so yes, so there were new. Okay, let's just stay on this one for 1 second here, and then go to the next one. So these are now heights for some fires that were occurring in Northwest Ontario just a week or so ago. I wanted to show a current example. So these are the heights here. Ontario, Canada, Northwest Ontario, these fires were occurring. The next slide, which is the last slide. So we used a model, in this case, the high split model, to trace where the smoke that had shown up on the 21st and the 20th and the 21st along the East Coast. Okay, that's shown at the bottom here. These are now measurements at the surface from surface observations. And you see this huge increase in smoke. So it's bad air quality in New York, in Boston, in Washington, D.C. We got it here. So tracing it back, we traced it with the model back to the source. And the source is what I was showing you in the previous slide, which were those fires in Northwest Ontario. So this puts all the pieces together, the ground-based measurements, the models, and the satellite data. And I thank you. I've raced through, I've gone a little over, but I hope I gave you a good picture of what we can do. Thank you.
Thanks a lot, Ralph. This is a very intriguing and informative and comprehensive presentation. So thanks a lot. I will stop the record so we can have some questions.